name is Dongho Lee, and I'm going to talk about the formalization of a programming language for quantum circuits with measurement and classical control. And the outline is, sorry. The outline is, I will give some brief context, and I will state more specifically about the problem that we want to solve, and we want to mention the previous research works, and then we move on to our works. First, the model of quantum computation we are based on is QRAM model. It has two parties inside, and one for classical computer, which does a classical computation and creates quantum circuits and transfer it to a quantum coprocessor. And the quantum coprocessor simulates a quantum process and returns the output of the measurement to the classical host. And one implication we want to consider, the quantum computation can now be a statistical set of quantum computation. So next I want to give some motivation for the work about the formalized circuit description language. And the objective we have here is that we want to analyze quantum programs before execution. First, we want to verify the functional correctness and safety of the quantum programs. But the reasoning and debugging of quantum programs can be non-intuitive. So we want to formalize by giving an operational and denotational semantics for the reasoning. And also we use type systems to guarantee the safety of programs. And another goal we have here, we want to optimize the quantum circuit in terms of memory and time. But the circuit can be large and complicated. And that's why we want to have a circuit description languages which can give a structured way to construct a large circuit and also give us a way to analyze quantum resources of circuits. In some elements of programming languages, we want to consider, first, we want to have circuit level operators like reverse and control. And also, we want to represent the families of circuits, which means a parameterized circuits. And we want to use the interaction between hosts and quantum coprocessors. And we want to have useful features like high order data types and recursions. So I want to give some ideas about the circuit description languages by giving two examples of them. First, Clipper is a high order programming language embedded into Haskell. And it has been used to implement various quantum algorithms. However, it lacks its own type system, which means that quantum programs can go wrong in Clipper. And there is also a Quire. It's also a general circuit languages, but it's embedded into Coq. And the properties can be proved using Coq's logic. And proofs also can be automatized using tactics, but it's not straightforward how to scale it up easily. Both languages allow us to construct circuits using classical computation and to run the quantum circuits by simulation, and also the transfer of classical data from quantum coprocessor to the classical host. And the last thing leads to the problem we want to solve. First, dynamic lifting is information transfer from the quantum coprocessor to the classical host, which is used in quantum circuit constructions. And now quantum circuit construction can be dependent on the result of measurement. So, and Clipper and Quire also implements a dynamic lifting, but they don't give a explicit formalization of the semantics. For example, in Quire, the operational semantics normalize the circuit constructions, but the classical control generated by the dynamic lifting is kind of hidden in the host term, in the box terms. And in Quipper, the operational semantics captures the notion of dynamic lifting, and it's embedded into monadic type system in Haskell, but the semantics has not been fully formalized yet. So to summarize, we compared the several languages, Quipper, Quire, Proto-Quipper, and us. Proto-Quipper here, we refer to the early Proto-Quipper by Neil Rose's PhD thesis, and we compared them in terms of circuit construction, measurement and dynamic lifting, classical control, and formal semantics and type systems. And I want to talk a bit more about Proto-Quipper because our works are highly based on it. It's a subset of Quipper regarding circuit construction, which is a formal semantics based on operational semantics. And it describes the interaction between host and quantum coprocessor by using two circuit operators called box and unbox. The idea of these two operators, box given a function, it creates a first class object called circuit, and unbox transfer this circuit object into the quantum coprocessor. And this language comes with the linear and non-linear type systems by using subtypings. And we move on to our work. For our work, the objective is to formalize the semantics for the interleaved quantum circuits and dynamic lifting. And the difficulty is on how to analyze the structure of a computation without simulating the measurement. And we do that by making the circuits not only lists of gates, but the tree branching over the result of the measurement. This tree structure is, we call it quantum channels. And in this perspective, dynamic lifting is a generation of multiple control flows in quantum computation, each of which is interpreted as a quantum channel. Our contribution is we give type languages extending quantum lambda calculus with box and unbox operators and quantum channel constants. And we give operational semantics that formalizes a dynamic lift in quantum circuit constructions. And this work is based on the Proto-Quipper as mentioned earlier. So to give some more detail, I want to give some how we define the quantum channel constants. First, we define a quantum channel algebra called QCL with those 5 constructors. The first one for the empty quantum channel, and the second, the unitary gate operation, and followed by the initialization and measurement and free qubit. Here, measurement, it's the one that creates a branching in our structure, tree structure. And then we move on to define the accessible quantum channel, which is just a pair of a quantum channel object and a tree of a binding function. Binding function that links variables to the wires of each branch of the quantum channel. And then quantum channel constant is a tuple PQBM as shown here. P here is a pattern of the input of the quantum channel, and M is a term which will be defined next slide. And B connects the free variables of the term to the wires of each branch of the quantum channel Q. And lastly, we define a type Q10 for the quantum channel constants. So now we want to define a syntax and a type systems. Here the term regarding the term quantum computation is now become a statistical set of quantum computation, and for this we have a bit extend the terms which we call the branching term. In the language, we can see the term defined as similarly to the quantum lambda calculus or the product keeper, and we extend these terms to the allowing it to branch, which represented as a square bracket in a branching term. And we define the linear type systems, which means that we ensure that variables are used exactly once in each branch of control flow. And the typing rules ensure that the term in the branching term share the same type. And here are some two examples of typing rules regarding the circuit operators. Now we define the operational semantics. We have two operational semantics, one for the circuit buffering and one for QRAM based. And circuit buffering is an abstract machine that creates a quantum channel, reducing the term. So the configuration becomes a pair of an accessible quantum channel and a term. And so we give a graphical representation for the configuration as shown in this figure. We can see the green box representing a quantum channel and box terms right, and the wires, the edges represent a bundle of wires. And the labels are for the variables and wires. And for the QRAM-based operational semantics, it's expanded from the circuit buffering configuration with the quantum registers called phi and L. So it simulates a quantum channel generated by the circuit buffering operational semantics. And because of the measurement, the reduction becomes a probabilistic relation, and the accessible quantum channel is generated according to the circuit buffering operational semantics. So now we give some examples. First, we want to show how we formalize a measurement in our language. Measurement is a constant defined as here. Its behavior is it creates a state for each outcomes in the classical computation. And in the quantum side, it adds a measurement gate. And you can see the measurement X term reduced to the quantum channel, including measurement inside with two terms. And we can go on to a little bit more complicated examples. EXP here shows a program that we measure a variable called VC, which is a qubit. And depending on its value, either we initialize a new qubit and delete the old one, or we just return the same qubit VC. One note I want to mention here is that this program has no corresponding circuit because of the classical control flows. And here it shows that how the operational semantics reduces the terms into a configuration here. And I want to conclude by summarizing. We have defined a simple language extending a quantum the calculus and product keeper, and we give a linear type system and formalize formalize by giving operational semantics, and for the validity, we prove the safety theorems for both operational semantics, and the future goal would be to extend the language with more interesting features like recursion and inductive data types, and we want also to introduce non-linearity to type systems. And this is all, and thank you for your attention.
Thank you. Are there any questions? One question that I have, I wonder if you could explain again, you mentioned, I know Quire has a notion of dynamic lifting, and as you said, there's this interplay between the operational semantics that reduces terms and then the denotational semantics for the circuits.
Yeah.
And I'm curious if you could say more about, now that we've seen your system, the relationship between your approach and that approach.
One difference here, to me, that Quire, the kind of this contour. So suppose we have a term like this in a Quire. I think, but we don't know the value of VC. So when we measure something, it's inside the classical host term in Quire, and it doesn't reduces to this kind of full configuration, I think. And here we can reduce this a bit further by allowing, by branching two terms that doesn't necessarily be calculated.
So it seems that it's sort of delaying. In Quire, it would be a bit more eager than in your situation.
Yes, it's, yeah. But it's only for the operational semantics. Quire, there is also denotational semantics so we can do by calculating matrix, can reduce it further to the denotational semantics. But here I was just saying the term operational semantic levels.
Okay, thank you. Any other questions? Okay, thank you very much.